So this is the last instructional video for this module, and then we have like a summary video with some examples to kind of reiterate these topics. And the good news is you've actually done most of this earlier when we were talking about proportions. So let's go back to this. Let's go back to this example with the 72 chronic cocaine users with the 3 treatment groups. One of them is a placebo, and we have a summary in our contingency table over here on the right. So if the person took the placebo, what's the probability that they relapsed? This is conditional probability. We're assuming the person took the placebo. We're only looking at how many people took the placebo. So out of all the people that took the placebo, what probability of them, what percentage of them relapsed? And this value right here, this fraction right here, is exactly the definition for conditional probability. Okay? I'll spoil it. It's right there. Probability of both divided by probability of the assumption. That's what we just did right here. Relapse with placebo, that's both, divided by how many took the placebo. But you can look at this a couple different ways. Again, let's relook at the question. If a person took the placebo, so again, we're only looking at these ones. This is what we're assuming. We're ignoring everything else. We're just looking at this row. If the person is in this group, what's the probability that they relapsed? And the answer is, well, 20 divided by 24. Well, let's kind of combine these two things. So if we look at this the old way, that would just have us jump to say 20 out of 24, or that should be 5/6. It's about 83.33%, I think. Or if you do it this way, you could say, okay, how many relapsed with the placebo? Relapsed and placebo, that's a joint probability. That's going to be, well, there's 20 of them that way. How many took the placebo? 24. Okay, you can see, right, these are the same. And there's kind of 2 different ways of looking at them. This way on the left is going to be using that conditional probability formula that we're going to talk about later on in this video. And on the one on the right, just pulls the numbers directly from the table like we did in the previous video. So let's do this again. Given that a person had lithium, this right here, this is the assumption. Given means assumption. Given that a person had lithium, what's the probability that they didn't relapse? So again, it's going to be very similar. Given that they had lithium, we're only looking at these people. Given that they had lithium, what's the probability that they didn't relapse? 6/24. Okay. That's 1/4 or 25%. Or again, you could phrase it. Oregon. I'm really on Oregon, our southern neighbors today, living in Washington. Given that a person had lithium, what's the probability that didn't relapse? We could also formulate it the same way. How many people had lithium and didn't relapse, divided by the total number of people who were taking lithium? I don't think I need a period right there. That's just another way of calculating the same probability. And that's conditional probability. So this is our definition right here. This is how we write it. The probability of A given B, where A and B are an event. So in the previous example, right, A is going to be they didn't relapse. We can think of that as event A. And B is the assumption, right? Given that event B has already occurred, that's going to be event B over here. So this value right here really is just the probability that they didn't relapse given they took lithium. And according to this formula, it's going to be the probability that they didn't relapse, and this is the intersection sign. It means and had lithium divided by the probability that they had lithium. So here we're using probabilities. I guess it's not exactly the same because here is just counting as opposed to, so it's very, very similar. So what's happening is when we do the calculations, we actually have a bit of redundancy. If we actually did it directly with this definition on the bottom, it would look a little different because I have too many things I want to talk about right now. But this thing up here, this is intersection. It's just another way of saying and. Like sometimes we'll write that symbol. They're equivalent. Okay. So again, this would be very similar. The probability that they had lithium and relapsed or and didn't relapse would be 6 out of 24 right here. So we could write that down, right? 6 out of 24 divided by the probability that they took lithium. That was 24 out of 72 people took lithium. And if you simplify this, things just cancel and we get almost exactly the same thing as before, right? We're dividing fractions. That's multiplying by the reciprocal. And then when we cancel right here, right, there's 124 goes into 72 3 times. 6 goes into 24 4 times. And you have, wait a minute. What just happened? I got a different answer. So this is a good opportunity to show problem solving strategies. Hey, totally intentional, right? So the probability of A and B divided by the probability of B, the probability, oh, here's what happened, is I was doing conditional probability on the top instead of total probability. In general, for total probability, the probability that in total that they have lithium and didn't relapse is 6 divided by 72. I was wondering why it wasn't canceling like I expected it to. So it's 6 divided by 72. So 6 over 72 times 72 over 24 when you multiply by the reciprocal. And now those 72s cancel perfectly. And we get that answer of 1/4 as we were expecting. Okay. So again, sometimes you'll get answers that you don't think are necessarily right. Kind of go back and go through and talk it through again and see where you got wrong. So again, it's just another way of getting that same answer. And that's why they're essentially equivalent. That's why they are equivalent, really, is because these 72s are always going to cancel. All right. So last but not least, here's tying in that these two definitions for independent and dependent events, multiplication and multiplication, they're essentially the same formulas, these two underlined formulas, because if these two probabilities are the same, if the probability of A given B is the same as the probability of A regardless, then those events are independent. This is one definition for independence. Let's go back to blue. It's a happier color. So this means that knowing that event B occurred does not affect or change the chance of event A. That's a typo. Okay, so let's do some more problems with this. Given that a person relapsed, what's the probability that they took the placebo? So given that they relapsed, let's call that B. What's the probability that they took the placebo? That's going to be A. Let's use this formula. The probability that they took the placebo, given that they relapsed, is the probability of both, again, that intersection or and sign, divided by the probability of B. So what's the probability that they took the placebo and relapsed? Took the placebo and relapsed is right here. Sorry. Took the placebo and relapsed is right here, 20 out of 72. Divided by what's the probability that they relapsed? Probability that they relapsed is going to be 48 out of 72. And again, just like last time, these 72s are just going to cancel out. And we're going to be left with 20 out of 48, which translates to 5/12. Oh, I have an email. 5/12, and as a percent, what is 5/12 going to give us as a percent? 41.6 repeating. Okay. And again, you could also do this the old way that we did in parts A and B. So is the treatment and whether they relapsed independent? Let's check the definition. Right? It's independent if the probability of A given B equals the probability of A. First off, I hope they're not independent. I hope there's some relationship between relapsing and getting treatment. Otherwise, this treatment is not working, right? So are these the same? Is this true? Well, the probability of A given B, we said that was 5/12. What's the probability of A? What's the probability that they took the placebo? Probability they took the placebo, well, a third of them took the placebo. Okay, so these are not the same. They're not independent. They are related. Okay. So given that they relapsed, it's more likely that they have the placebo, which is good. We want our treatments to be working. And that's conditional probability. We have some extra examples. If you're still feeling a little uncertain about all this stuff, check out the next video. Plenty more for you, plenty more math to talk about. And we'll do a little summarization with these rules as well. Good luck, and let me know if you have any questions.